Guys, in these two videos I'll be solving the odd numbered free body diagram problems. So this is part one. Part one I'll be doing the front sheet. So 1, 3, 5, 7. You're going to do the even numbered problems, but remember all the problems must be completed for full credit. Okay, so let's start. A 6-kilogram block lies motionless on a table. Draw and label the forces on the block, then calculate each of these forces. So it's motionless. That means the net force acting on the block is 0. Net force equals 0 newtons. So let's get those two forces. The first force we have is the object's weight, or the force of gravity. I'll label this W, or you can call it F sub G. Either way, it's fine. And then we have a force that opposes the weight. This force is equal and opposite to the weight, and it prevents the object from sliding through the table. And this is known as the normal force. You can call it F sub N or R. This is the normal force. And notice the normal force is equal and opposite to the force of gravity. This is in conjunction with Newton's third law. For every action, there's an equal and opposite reaction. So let's calculate the force of gravity. W, the weight, is 6.00 kilograms times 9.81 meters per second squared. I'm going to keep the forces, all the forces positive, and I'll just denote their direction with the arrows. So the weight is 6 kilograms times 9.81. The weight is equal to 58.86, I'll round this up, 58.9 newtons. And so equal in magnitude but opposite in direction is the normal force. It's the force that the table exerts back on the object, and that's 58.9 newtons also. Number 3, a 10-kilogram block slides at constant speed across a frictionless table. Draw and label the two forces on the block, then calculate each of these forces. Same thing. Motionless, constant speed. Either way, the motion is constant. So just like before, this object has its weight, which is 10 kilograms times 9.81 meters per second squared. The object's weight is 98.1 newtons. And now we know that the normal force is the force that the table exerts back on the object, F sub N, and that is also equal to 98.1 newtons. So far, so good. Next up, number 5, a 1.20 kilogram block is slowing down across a rough surface. Slowing down. Draw and label the forces on the block, then calculate each of these forces. The friction coefficient for this is 0.1. Note the friction coefficient is a unitless number. Engineers typically calculate these values to account for a loss of acceleration for objects that are sliding across each other. So we know the object is slowing down. That means the motion is not constant, it's accelerating. So we know that we have the object's weight, and I put this dot here to represent the object's center of mass. That's the point on which the force of gravity seems to affect. So weight is equal to 1.20 kilograms times 9.81 meters per second squared. I will do that in the calculator. 1.20 times 9.81, and I get a weight of 11.772, so I'll round this to 11.8 newtons. And it has a equal and opposite normal force acting on it, the F sub N, and that is also 11.8 newtons. And then it has this third force, this force of friction. This force of friction is a contact force as well, and it occurs when real objects rub or slide, move with respect to each other. So, and I'll label this F sub F, force of friction. We have an equation for the force of friction. Force of friction is equal to mu times the normal force. In this case, the mu is the friction coefficient. This is the Greek letter mu, like mu, or like the Pokemon Mewtwo or Mew. Okay, so mu is 0.1. It's a unitless number. So the force of friction is 0.1 times the normal force, which is equal and opposite to the object's weight, or the force of gravity. So 0.81 times 11.8 newtons. This gives me a friction force, 0.8. Well, this is just divided by 10, so 1.18 newtons for the force of friction. So I do want to box these in, so I want you to box in your answer. Sorry, I have not been doing that, but just to make it easy for me to see and so you know yourself what you've done, go ahead and box in your answers. Okay, next, number 7. A 9 kilogram block slides down a frictionless incline. The angle of incline is 35 degrees. Label the forces and calculate these. Find the acceleration of the block. It is a frictionless surface, so that's helpful. So this is where we get into breaking our weight of gravity into its components. So I will start by drawing the very first vector you draw, and that is your weight, which is the force of gravity. Oops, I'm sorry. And the force of gravity is equal to 9 kilograms times 9.81, and that is 9 times 9.81. So I get a weight, the object has a weight of 88.3 newtons. I'm rounding up 1 decimal place. Okay. Now this is a 35-degree angle of incline. You need to know that this weight is now acting on an incline, which means that the component, this weight vector, is going to split into 2 components. One component is perpendicular to the surface of the incline, and it gives rise to the normal force. Let me draw this the same length if I can. So this force normal comes from this component of the weight. The other component of gravity splits parallel to the surface, and I'm going to call this pink vector force down. It's the force that is responsible for sending the object down the ramp. So we take this weight vector, we split it into a component that is at a 90-degree angle perpendicular to the surface. It gives rise to the normal force, and then we split it into a component that sends the object down the ramp. And all I'm going to do is translate that pink vector right up here. It's the exact same vector, but it's the reason why objects slide down ramps. And they slide down ramps slower than if you were to drop them. And it is because the weight can't send the object through the surface of the ramp, but it gets split into these 2 vectors. One of the vectors sends the object actually down the ramp. And I'm actually going to redraw this vector triangle. I'm going to draw it right here so you can see this is my weight. I want you to look at the weight like it's the hypotenuse of a right triangle. We have this vector that tries to send the object down. This is what I'll call F down the ramp. And then we have this vector, and it's equal in magnitude, opposite in direction to the normal force. So I'll call it negative F sub n. These two make they're at right angles with each other. So, and also you will just know that this weight, the angle between the normal force, the F sub n, and the weight is equal to the angle of incline. When these vectors, if this was a flat surface like this, you can see that there's really no angle between these. Okay, yes, they're 180 degrees apart, but really they're right on top of each other. In this case, I've rotated the surface, and so now there is a 35-degree angle acting between these two. It's the same as the angle of incline. So we can calculate the force down the ramp, knowing that this force down the ramp is opposite to the angle, so this is our opposite side. Knowing that the weight is the hypotenuse of this vector triangle, and knowing that I have theta, an angle. Opposite hypotenuse, this is a sine function. So sine of the angle, sine theta, is equal to the opposite side, the force down the ramp, divided by the hypotenuse, which is the weight. So now I plug in. I'm going to solve, well, first I'll solve for the force down. I'll multiply the weight on both sides of the equation. Weight times sine theta is equal to the force down. So let's calculate. We already have the weight. It's 88.3 times sine of 35 degrees gives me my FD, my force down, and that is equal to 88.3 times sine of 35. Make sure your calculator is in degrees, and I have 50.6 newtons for the force down. Okay, now we're going to get the normal force. The normal force is equal in magnitude, opposite in direction to this purple line right here. Notice that this is adjacent to the angle. I have an adjacent side. I have the hypotenuse. Adjacent, hypotenuse, so TOA. This is a cosine function. So the force, cosine theta equals the normal force divided by the hypotenuse, which is the weight. If I solve this for the normal force, W times cosine theta equals the normal force. Same thing, I will calculate now. 88.3 newtons is the weight times cosine of that 35 degrees is equal to the normal force, and that becomes 88 times, make sure again your calculator is set to degree mode, and I get a normal force of 72.3 newtons. Okay, and now we want to find the acceleration of the block. Please note there is one net force acting on this block. This component of gravity is equal in magnitude, opposite in direction to the force normal. It actually gives rise to the normal force, so they cancel out. All that is left is the force down. Note this is the exact same force, these two pink arrows. I've just translated this vector up here. So the force down is the net force. And we know Newton's second law, F net equals m times a. So to get the acceleration of the object, I'll use a different color. Acceleration for this object is the net force, which is our force down, 50.6 newtons, divided by the object's mass, 9.00 kilograms. So I do this 50.6 divided by 9, and I get an acceleration of 5.62 meters per second squared. Okay, so you'll do this process for this one. Just note the process. It doesn't change. The weight vector is always the hypotenuse for your vector triangle. I hope you found this video helpful. Join me for part 2, where I go over the next 5 questions, or the next 4 questions. Thanks for watching.